Virial Theorem. This famous theorem states that the average kinetic energy of a system of bound interacting particles is related to the average potential energy. Let's prove this famous theorem. First, we write a quantity G, which is defined as a sum of dot product of all momenta and positions of all the particles. Let's find full time derivative of this quantity G. We use the rule of differentiating a product and we get two terms. Next, we're gonna average this quantity. In other words, we're gonna find a time average over period tau, which is given by this quantity G evaluated at time tau minus G evaluated at time equals 0 divided by tau. Since we are taking an average over long periods of tau, it's easy to see that for a bound system, this quantity will tend to go to 0. Thus, we get the following result, that a long time average of G dot is 0. This requirement can be relaxed, that we are taking the average not over long periods of time, but rather over a large ensemble of particles. So what does it mean that average of G dot is equal to 0? We can write it explicitly. On the left hand side, we can write sum over product of momenta times velocities of each particle. And on the right hand side, we can write minus average of sum of all the particles of product of momentum change times individual particle position. We can identify some of these terms. This here is the force acting on each particle, and this here is 2 times kinetic energy of each individual particle. Thus we continue to write that average of kinetic energy is given by minus 1 over 2 of an average of the following sum: force acting on each particle dotted with position of each particle. The quantity on the right is known as virial. In order to apply this theorem, we have to be able to compute virial. So for this, we need to know the form of the force. For example, if force is a radial function to some power, and therefore the potential energy is given by some constant times r raised to power n plus 1, then to compute virial we can write r dot gradient of potential energy, or along the radial component it's going to be simply r times derivative of du with respect to r. It's going to be constant k times n plus 1 times r raised to power of n plus 1, which is, as we see, simply n plus 1 times the potential energy u. Therefore, in this case, Virial theorem is rewritten to say that average of kinetic energy is equal to n plus 1 divided by 2 of the average potential energy. One example that we encounter a lot is force when n is minus 2. So the force scales as inverse squares of r, in which case we get that the average kinetic energy of particles moving and interacting with such a force will be minus half of their average potential energy. We will see that this result allows us to solve a number of problems in a very elegant manner.